Good afternoon, everyone, and welcome to quantum computing. Today, we already have the lecture on a Thursday afternoon or evening, so there are not that many in the live stream. Hopefully, more will join, but we'll have the recording anyway. And next week, the lecture will take place at the usual slot on Fridays. I always start with a quick summary of the past lecture. So last week we had our first session of the quantum computing course. We discussed how we can speed up an algorithm, looked at some approaches, and then saw how quantum computing or why quantum computing looks promising to solve certain computational problems substantially faster, because using quantum mechanical principles, we can solve some of these problems in a better complexity class. That's what we saw, and we saw also that quantum mechanics can be seen quite independently of physics. In fact, it's a generalization of probability theory. And we looked at one concrete problem, the black box search problem. And we saw that with a traditional computer, we need O of n time, but using the Grover's algorithm, we can solve this in O of square root of n. And we looked at some sample architectures like from D-Wave, and I provided a quick overview about the objectives of the course and the prerequisites and the organization. I saw there was already quite some discussions in the iLearn forum about the presentation and if this was a project or not. For now, maybe don't think much about the presentation because right now, it's too early to grasp this because we first need to lay the foundations, and in a few weeks' time, we'll talk more about the presentations. Then the marking of the presentation of this will also come later. I provided some book recommendations and talked about some of the recent news like this one here or the new standards that have been released for post-quantum encryption. We looked at some further reading that I expect you to read, like this chapter from Daniel, as well as if you're curious to get the bigger picture of my preprint or a preprint of my upcoming book chapter. And then Horst Kuhnhardt talked about the history, compared quantum computing, more traditional computing, provided an overview about some architectures and some business potentials. And Horst will talk more about this in chapter 8 in a couple of weeks when we look at concrete quantum computer architectures and how to program them. Then we started laying the foundations for the rest of the term. In particular, we looked at complex numbers with a quick intro or a quick revision, depending on your previous knowledge. And we need complex numbers for this course, the whole course. They are essential to describe our quantum mechanical effects. And then I left you with a little quiz when we try to calculate I to the I. Between these two steps, I said there's something you need to be thinking about, how we get from ln I to this one here. In fact, I is a complex number, so it just has the imaginary part. You can plot it in the complex sphere, also something we looked at. And then you can try to describe this I in terms of the Euler notation, where the radius or the distance is 1, and then it's e to the I with an angle. And you need to see how you can rotate to get to I concretely. That rotation is pi half anti-clockwise, and you have e to that, but then you take the logarithm of that Euler representation, and then the first part is the radius plus this one here. So if you didn't get that last time, maybe you have enough hints now to make it from this step to that step. It isn't that difficult, and we've discussed all the other steps. So just see the complex plane for I as well as the Euler representation. And we finished the complex numbers last time, and today we will quickly revise vector spaces, concretely vectors and matrices and all of this. And we'll revise this for real numbers, and then we start putting complex numbers in these structures. And then we have all the foundations we need to describe quantum mechanics for the rest of the course. Just as a brief reminder, you have seen this before, like in a Maths 1 course, that you have this R for the real numbers, the set of real numbers to the n. That concretely refers to the Cartesian product of R with itself n many times. You've seen this before. It's just a quick revision because we will need this notation now a few more times. And we will very briefly revise some fundamentals in linear algebra now, like vectors and matrices and some of these operations. And then we will first do this for the real numbers, and then we're going to do this for complex numbers, and there will be some new concepts, and then we can start working on quantum systems. For this revision, again, the book that I talked before about quantum computing for computer scientists is a great book to get this revision or thorough introduction, whatever, in case you haven't seen these concepts. Has any of you started looking into the book Quantum Computing for Computer Scientists? If so, maybe just raise your hand or thumbs up or down in case you have not. And I will switch to the iPad briefly. So, what we will do now is we will briefly look at vectors and then at matrices. So, we will have vectors, and vectors are actually from the type of R to the n, because a vector has n many elements of real numbers, and we can add vectors, we can calculate their length, whatever. So we may have a vector A with the elements 1, 2, 3, and vector B 0, 5, and 7. And you can add A and B. So you just add the elements step by step. So 1 plus 0 is 1, 2 plus 5 is 7, and 3 plus 7 is 10. You can also subtract vectors, you can invert vectors, and you can also calculate their length. So the length of a vector is often denoted as something like this. And what you do is you take each element value, you square it, and you sum these squares together, and you take the square root of this, and then you have the length of vector A. So we can calculate this. It's 1 plus 4 plus 9. So it's the square root of 14. This would be the length of A if you see A from a geometric representation. And this brings us also briefly to the geometric representation. Imagine we have a vector Z, which is 2, 3. Then you could also try to plot this or see it from a geometric perspective. We have the first component and a second component. So you could say this is component 1, this is component 2, and then 2, 3 would be somewhere here. And we could visualize this vector, and the length of the vectors, or the length of C, would be the square root of 2 squared plus 3 squared, the square root again of 4 plus 9 is the square root of 13. That's the length of this vector. And if you have any questions in between, if there are certain things you don't remember, obviously let us know. There are all sorts of other operations you can do on vectors. You can multiply a vector with a scalar. For example, you can say 2c. That means you multiply 2 with every element in the vector. So this would be 4 and 6, because we had c here, and then 2c would be 4, 6. And you can do other operations on vectors. For example, we have, let's say we start with new vectors. So A is 1, 2, and 2, and B is 2, 0, and 4. And what you can also do is you can take the an operation that has multiple names. which technically are slightly different things, but with vectors, typically it's just the same. It's the dot product or the scalar product. So you can take the scalar product of A and B, and what you do is you multiply the elements with each other, and you sum together these products. So 1 times 2 plus 2 times 0 plus 2 times 4. So this is 2 plus 8. This is 10. There are all sorts of geometric interpretations of what all of this can mean, depending on the context, but it's just a fundamental operation we see very often. Are you all okay with vectors up to here? Maybe just thumbs up or thumbs down if this is all something you feel okay with. So please use these reactions here in Zoom that I can see, but should be all okay. But it's important we quickly revise it because very soon we're going to put in complex numbers and then we need all of this. There's also so-called vector spaces. For this, I'm unable, just at this very short time, provide an in-depth revision of vector spaces, but vector spaces have a dimension and a basis. Typically, say for a three-dimensional one, the basis vectors would be something like this. But you can have a different basis as well, and you can convert from one basis to the other. It's something we will see later in this course with quantum mechanics when we come across the concept of a basis. And there are lots of other things, obviously, one can do at this point. But if you're not familiar with bases or dimensions or whatever, please just look up the books for a more thorough revision, because you should have learned all of these concepts before. One extra note, because we will need this, C up here, for example, we call this a column vector because we have the values in this column. We can also have a row vector, and concretely we transpose this vector, and then it's a row vector, and oftentimes would be written as something like this, or with brackets. So it's a row vector, and we just transpose the column vector to get a row vector. We can transpose a row vector to get a column vector, and so forth. And these are concepts we will also need now for matrices. So a matrix is a structure, say from the real numbers, of m times n. That means a matrix has m many rows and n many columns. And a sample matrix could be, for example, something like this, say 2, 1, 0, 4, 0, and 1. Oftentimes, matrices are denoted by capitals, like here, a capital A, a capital B would be another matrix, a 0, 0, 5, 1, -2, and 0. And we can add matrices if they are of the same size. So we could say A plus B, and then we just add these elements piece by piece. So 2 plus 0 is 2, 1 plus 0 is 1, 0 and 5 is 5, 4 and 1 is 5, and 0 minus 2 is -2, and 1 plus 0 is 1. You can also subtract them, and so forth. You can transpose a matrix also. So for example, we can transpose A, and eventually A will look something like this, or A transpose, it's 2, 4, 1, 0, and 0, 1. Also a very fundamental operation. And what you often see is, I'm unable to write this in a smart way here. Oftentimes in the literature, vectors are written in lowercase but bold, so but I'm just unable to write this in a proper bold way. And the matrices are uppercase but also bold. You do this to distinguish them from scalars, because a scalar like 2 could also be a variable, and the scalars just use the regular font. Bold ones in lowercase are vectors, uppercase bold are matrices. It's often denoted like this in the literature. However, the course book we're using, Quantum Computing for Computer Scientists, does not do that. And so I've also avoided using bold symbols in this course as far as possible because I just want the course to be quite close to the course book. Something I'm not too happy with the course book, lots of other literature uses bold symbols, but we still use uppercase for matrices and lowercase for vectors. Then we can also multiply matrices. Imagine we have a new matrix that is now 2, 0, 1, 5, and B is another matrix, 1, 2, 0, and 2. And I want you to multiply A times B. It's very important to keep that order, that it's A times B and not B times A, because this is not commutative. This is a quick revision for you if you remember how to multiply matrices. And once you have the result of multiplying these two matrices with each other, please share the result in the chat. And then I'll also try those calculations. And I'll be happy to compare my result with your result then. So we got a suggestion. We'll see. A notation that I often use to do this is this one here. So A is 2, 0, and 1, 5. And B is 1, 2, and 0, 2. And then in order to calculate this, we have this row and this column. And we take their scalar or their inner product. So it's 2 times 1. So 2 plus 0, then it's 2. This is the first element. So just highlight these 4 elements. Then we can, this one here, this row with the first column, it's also 1 times 1, because you need to say 1 times 1 plus 5 times 0. It's 1. And then for the next column, it's 2 times 2 plus 2 times 0. It's 4. And the last one here is 2 times 1 plus 5 times 2. So it's 12. The suggestion here in the chat is correct. Are all the others of you fine with multiplying matrices? Maybe just, again, thumbs up or thumbs down if this is something you feel okay with. Because it's your course, so if you need any revisions, let us know, and I'll be happy to help you with that. Maybe some more reactions from the attendees, whether you're okay with multiplying matrices. It's important you multiply them in this order. In the other order, you will get a different result usually because it's not commutative. And obviously, to multiply matrices, they need to be in dimensions that fit. A few more concepts. So we've seen transposes. The determinant is also something you may come across, determinant. And for example, the determinant of this matrix here is a 1, 2, 3, and 4. And the determinant, who of you remembers how to calculate the determinant of a 2 times 2 matrix? If you have the result, if this is something you remember, send us this in the chat. Still waiting for your responses in the chat, whether you remember how to calculate the determinant of a matrix. If you don't remember this concept, maybe just send a thumbs up or something, then I'll know whether we're on the same page or not. Or well, we got a thumbs up. Someone who remembers, then please send the result here in the chat. So one student suggests -1. Well, we take the product of the two elements in the first diagonal, so 1 times 4, and we subtract the product in from the other diagonal, -3 times 2. So it's 4 minus 6, it's -2. You can also calculate the determinant of larger matrices with various algorithms, and the determinant is something you can, for example, use to determine or to see if a system of a linear system of equations is solvable, if it has one solution, if it has infinitely many solutions, and there are lots of other applications of the determinant. And you may be seeing some of them in this course or when you read papers for your seminar presentation. So that's why I quickly wanted to revise the concept of a determinant. Then there is another concept. It's the trace of a matrix. Who of you remembers what the trace of a matrix is? If you remember it, thumbs up. If you don't remember it, thumbs down. Only see thumbs down. That's fine. So if you have a matrix, say 1, 0, 5, 7, 1, let's say 2, -1, 9, 10, 11, then the trace of this matrix would be the sum of the elements in the first diagonal. So if we say trace of this matrix, then this would be 1 plus 2 plus 11. So 14. Also a concept we may be needing later in this course, and it's just a sum of the elements in the diagonal. So this is the trace. And we're almost done. Just a few more concepts. We have the inverse of a matrix. Who of you remembers the concept of an inverse? Maybe thumbs up or thumbs down. I see positive reactions, but we'll quickly do it. So you may have a matrix A, and you multiply it with its inverse, the same as the inverse times A, and this will give you the identity matrix. And the identity matrix, so I, say I3 as an example, it's a 3 times 3 matrix, which only has ones in the first column and zeros everywhere else. So this would be I3, I4 would be 4 times 4, and you only put ones in the diagonal. All the other elements are 0. You can use that concept of inverse also for solving linear systems of equations and so forth, and all sorts of other concepts to undo operations. And very soon we'll see a related concept when it comes to complex numbers in linear algebra. We'll introduce something that looks like a bit like the inverse, but it's a different operation. And then the last revision are eigenvectors and eigenvalues. Who of you remembers them or has come across this concept before? Thumbs up, thumbs down. Some don't remember, that's perfectly fine. I'll show you this. There's a good example in the book. If you imagine you have a matrix, and one thing is important, not all matrices can be inverted. That's important. Some can, but some cannot. And in an intro to linear algebra, you discuss in detail when a matrix can be inverted and when not. And now we have this matrix here. So we call this matrix M. And this matrix has some interesting property. We see matrix M, so it's a 2 times 2 matrix, and we multiply it by a vector, 1, 1, because we can multiply vectors with each other, we can multiply matrices with each other, so we can multiply matrices and vectors if they fit, because eventually a vector is just a matrix with one column. And we can multiply them, and just for you as a revision, maybe you can take this matrix and multiply this vector here from the right. And once you have the result that you get out of this multiplication, send it here in the chat. We'll just again as another revision, and we already got the right answer. It's 3, 3, because I have this these ones here and here, so it's 4 times 1 minus 1 and 2 times 1 plus 1, so it's 3, 3. And here we can factor out the 3, and it's 3 times 1, 1. And we see something interesting, like we took 1, 1, and we multiplied it from the right with this matrix, and we got 3, 3, or 3 times 1, 1. And we can also try to visualize this from a geometric perspective. Imagine we have our, well, maybe too long, we have the vector 1, 1, and we multiply it with m, and we get vector 3, 3. Same direction, but longer. And concretely, this means that 1, 1 is a so-called eigenvector of matrix M, and factor 3 is a so-called eigenvalue. As we see, 3, 3 is the same direction as 1, 1, it's just longer. And if it's longer or shorter, it could also be shorter. It could be like 0, 5, 0, 5. Then the eigenvalue would be half. You could also have, say, minus 2, minus 2. Then it's just inward. It's just the opposite direction. Then the eigenvalue would be minus 2. And we see that 1, 1 is an eigenvector of matrix M. And we've seen a geometric perspective of this. There are various ways how you can get the eigenvectors and eigenvalues from a matrix. This is something you should have learned in an intro to linear algebra, so we're not revising this. But this concept of eigenvalues and eigenvectors will be crucial later in this course for some of the more advanced topics. So we have now done an introduction to, or just a quick revision of linear algebra with real numbers. And now we can apply this exactly the same to the complex numbers. And as we denote the real numbers with a R, these complex numbers are denoted with a C that looks something like this. And then we can say that vectors are actually from the structure C to the n, because it's a set of complex numbers, and we have n many in that structure. And we can try this out now, and we can see what it looks like. For example, we have say a small v. The first vector has elements 6 minus 4i, 7 plus 3i, and minus 3i. And then we have w, another vector, which is 16 plus 2.3i, minus 7i, and minus 4i. What I'm doing now is complex linear algebra. And all I'm doing is I have linear algebra structures, and I don't put in real numbers, but I put in complex numbers. Has any of you done something like this before, that you take your linear algebra and you put in complex numbers? Maybe thumbs up or thumbs down if you have done something like this before. It's something I have definitely not done in my introduction to linear algebra when I studied. I only came across this later in my career. And it's crucial now to describe quantum computing or quantum systems in the first place. And it's quite interesting because we can plug in complex numbers, and most of the linear algebra just works as before, but we're dealing with complex numbers. It's a little bit difficult to find a lot of literature on complex linear algebra. So I have like 3 or 4 introductory books to linear algebra at home, and I think only one of them covers a little bit about complex linear algebra. Most of the standard or most of the linear algebra textbooks don't cover this a lot. So that's one thing I noticed after all these years. And now we can see we can add V and W. And actually, we're just adding 2 complex numbers. So what I'm doing is I add the 6 and the 16, so it's 22. And I have 3.I and minus 4I, so it's minus 1.7I. You can just go ahead with the next 2 elements of each of the 2 structures, and you can sum them up and write the result in the chat. What happens if you add the second and the third elements? So 7 and then 3i minus 7i minus 4i, and here minus 3i minus 4i, it's minus 7i. So not too difficult. And all the stuff we have just done before works exactly the way for complex numbers. So we can have matrix additions, we can multiply matrices. We're just multiplying complex numbers, and we've seen this last time. You can calculate the trace, lots of other things. The only thing that works slightly different is actually finding eigenvectors and eigenvalues. This is a bit more tricky for complex numbers, but we don't study this now by heart or in detail. It's not necessary for the course that we manually know how to find the complex eigenvalues and or eigenvectors and eigenvalues. That's slightly different, but all the other concepts are pretty much the same, like transposing, multiplication, addition, and so forth. If you want to study this in detail, and also the length of a vector, and the scalar product and so forth, all of this is just the same, but we deal with complex numbers. So last slide was that we finished was this one here, just some important concepts that we have revised in the last half an hour. When you do this with complex numbers, all of that is the same as I just said. Eigenvalues, eigenvectors is a bit more tricky, but that doesn't matter for now. But there are some new concepts that we need to look at now for today. Concretely, we look at 3 new concepts when it comes to complex linear algebra. We will study the conjugate matrix, the adjoint matrix, and we study unitary matrices. And once we have studied that, this will now take maybe 20 minutes or something like this, we will look at another linear algebra concept, which are tensor products. And then we have all the maths needed for the rest of the course. And we only need to apply it to ever more complex systems, starting with some deterministic systems, then probabilistic systems, and then quantum systems, and then we build quantum algorithms. So we're almost done with all the maths we need in this course. And that it's more fun and more interactive, I'll show you this again on the iPad. So it's not just looking at math slides. So we have a matrix, say, we have a matrix A, and we have something that is called A bar. This is the conjugate matrix. It's all well typeset in the slides. You remember the concept, the conjugate concept of complex numbers. This just meant we are inverting the sign of the imaginary part, and we can apply such a concept also to matrices. Imagine we have a 2 times 2 matrix, which is called A, and we have elements A, B, C, and D. And a conjugate matrix is again a 2 times 2 matrix, and these elements A, B, C, and D, they are now complex numbers, not real numbers. We can calculate this conjugate matrix taking all these elements and taking their conjugate. And in order for this to be more clear, I have an example. Don't look this up in the slides, otherwise you see the solution early, but I want to practice this with you. So it's 6 minus 3i. The next element is 2. Then this element is 9i. Then minus 2 plus 4i. And now the conjugate matrix, I'll start with the first element. It's just 6 plus 3i. Because all I'm doing is changing the sign of the imaginary part. And now you can go ahead calculating the remaining 3 elements and providing them here in the chat of what the conjugate matrix of A would look like. So you can try this. And if you have any suggestions, just put it in the chat. Just put it in the chat then. So I'm still waiting for some responses here in the chat. I'd be very happy to see any responses of what these next elements would look like. If you have so we got the next one. So the 9i would be minus 9i. This here would be minus 2 minus 4i. And the 2 just stays the 2. Because it's just the real part. So we have just calculated a conjugate matrix, and you're probably wondering what is that useful for. We will now introduce a fundamental matrix concept, which is called the adjoint matrix. And the adjoint matrix of A is denoted as something like this, with this cross up here. And this is pronounced as a dagger. It's a dagger, in fact, not a cross. And if we have a matrix A with complex values in it, then we can calculate its adjoint matrix A dagger. And I'll show you what it looks like. So we have a matrix A. It's again 2 times 2, but you can apply this to other matrices of size 3 times 3 and so forth. So it's not constrained to 2 times 2. So we have a matrix A, B, C, and D. And then its adjoint matrix is again A and D conjugate. But we not only calculate the conjugate values, but we also transpose the matrix. So you have seen we flipped B and C, and we have the conjugate of each element. So this is then the adjoint. So just like the conjugate matrix, but we also transpose it. And just to make sure we're all okay with this, just take the matrix from before, which was 6 minus 3i, 2, 9i, and minus 2 plus 4i. And I want you to calculate the adjoint and send the 4 elements here in the chat in our Zoom session, ideally in the right order. So you would start with the first element, then the second element, and the third, and then the fourth. So we're all on the same page. And remember, it's just the conjugate matrix, but we also transpose it. So it's again 6 plus 3i. And the last element is as before, minus 2 minus 4i. And then these two here get flipped. So it's minus 9i and 2. This is the concept of the adjoint matrix. And you're probably wondering, what is all of that useful? There are so-called unitary matrices, and these unitary matrices, we'll see them maybe later today. I'm not sure how quickly we are. I'll say at the latest, we'll see them next week again, which I know the singular unitary matrix. And U is unitary. So U is a matrix with complex values in it. And U is unitary if the following relation holds true. U dagger times U is the same as U times U dagger, and that is also the identity matrix. So if I multiply U dagger with U and U with U dagger, in both cases, I must get the identity matrix. Now, this is one of the fundamental types of matrices we need later in quantum systems, because what it allows us to do, if we describe a transition in a quantum system with a matrix U, and it's a unitary matrix, we can use U dagger to undo that operation. So we do an operation and we can undo it. And this is something super important in quantum mechanics and later for quantum computing, because if we do a calculation, we can undo it. And this is crucial for a lot of algorithms, as we will see in the coming weeks. So we need all of this maths. And now you're wondering, what is one example of a unitary matrix? One that we will see super often, and I think Horst last week mentioned it very briefly. It's the Hadamard matrix. It's a matrix that will keep us super busy when we look in detail in quantum computing operations. And this Hadamard matrix looks something like this. And if you now want to calculate its adjoint matrix, you will see it's actually just the same. So this factor here is just a factor for all the elements. So we just move it out that the matrix actually looks cleaner and simpler. And H, now these are only real parts in here. No complex part or no imaginary parts yet, but there will be more complex matrices coming later. But H is a unitary matrix, and it's actually a super important matrix in quantum computing to describe one of the most fundamental operations in the beginning of quantum algorithms, to actually create a superposition. That means that we actually turn a classical value into a quantum value, so we can take advantage of parallelization. And you can try out at home, and it isn't that difficult, but it's one of your tasks at home to calculate h times h dagger, and you will see that this in fact gives you the identity matrix 2 times 2, and it's obviously the same if you do h dagger times h. But this is your homework for at home. It's not very difficult. In fact, you just need to take care of this factor here, and it will work out, and you will see that this is a unitary matrix. Could you think about an even simpler unitary matrix? What do you think is maybe the simplest unitary matrix possible? If you have a suggestion, maybe just raise your hand. If you cannot think about the simplest unitary matrix possible, maybe thumbs down. We got the right answer from here in the chat. The identity matrix, is just the simplest one possible, because if you have I dagger, it's just I times I. It's obviously I times I dagger, and that's I. So it's just the simplest unitary matrix possible. These are now some new concepts that we need in complex linear algebra. So just as a revision, we started with the conjugate matrix, where we calculate the conjugate, each complex number, and then the adjoint matrix. We do the same, but we transpose. And then we have unitary matrices, which is a fundamental property of matrices we need later on, so that U dagger times U is the same as U times U dagger, and both is the identity matrix. We will switch back to the slides briefly, because all the concepts I have shown you are also super well formatted in here in the slides. And just for your revision, there is one concept left, and I'll just show this in the slides because it's a little lengthy to write it down on the iPad. It's a so-called tensor product, and the tensor product is another foundation from linear algebra. In fact, it's not constrained to complex vector spaces. You can use the tensor product for any two vector spaces, V and W. So we have two vector spaces, V and W. It's important they need to be over the same field, otherwise they wouldn't be compatible. And if we calculate the tensor product, we often use this symbol here. It almost looks like an XOR symbol, but it's rotated by 45 degrees. And so we calculate the tensor product of V and W, and this creates a new vector space that can often be interpreted as the space of all tensors that can be built from vectors from its constituent spaces. And we're using an additional operation that can be considered as a generalization or abstraction of the outer product. What does that look like? You will now see soon a slide that looks super complex, but it's actually not that complex if you look at it. And I'll also tell you in a moment why the tensor product is super important to this course. Say we have two times two matrices, so we have A and B, and we denote the element here A11, A12 for the first row, then the second row A21 and A22, and we have our matrix B. We can calculate a tensor product. Concretely, the tensor product will lead to a matrix that is of size 4 times 4, and we'll create it the following. We take our value A11, which we can now see as a scalar value, and we multiply it with our matrix B. So this, when we put the matrix B in here, it leads to 4 elements. Then our value A12 from before is a scalar that we multiply with b and put b in here. And we do the same for a21 and a22. And then we multiply a11 times b11, which is this element. Then a11 times b12 is this one, and so forth. So it looks more complex than it actually is, because all we are doing is we are creating a larger matrix than before, and we take each element from the left matrix and we multiply it with every element in the second matrix. Looks more complex than it is. Now you're wondering, has any of you ever seen the tensor product before in a course? I don't think it's typically taught in an introduction to linear algebra, but if you've seen it before or not, maybe thumbs up or thumbs down. What is it useful for? So one person has seen it before. Maybe you can let us know where you have seen it or what you have used it for, either in the chat, or you can turn on your microphone and tell us more where you have used the tensor product before. We're most happy to hear what you have done or what you have used it for. Just give you a second to respond. And meanwhile, I'll say a few words. The tensor product is needed in quantum mechanics when you want to combine multiple systems. So you can imagine like one qubit, one of the fundamental units in quantum computing, and you want to have this one qubit be connected or not combined, or you have an operation of one qubit and another qubit. And for that, you may need a tensor product to build that vector space in which you're operating. But we'll see this in probably in 2 weeks or something, or maybe next week already, depending on how fast we progress. Probably next week already, we'll see the tensor product. And one of the responses here in the chat is that the student says it's related to the Kronecker product and used it in a certain algorithm. Feel free to look up that word Kronecker product and see how it relates. The tensor product here looks very abstract, but in the next chapter, we will already need it concretely at the end of the next chapter when we assemble quantum systems, because we will have simple quantum systems and we want to assemble them together, and we can describe this with the tensor product. I know this was quite some maths now in 1 hour or 50 minutes as a revision or intro, but the best way to actually understand this now better is to apply it. If you want to do further readings, you can look into chapter 2 of the textbook, Janowski and Minucci, which cover this in detail and with lots of examples and explanations. But since you have all come across linear algebra before, I think this very quick revision here and coverage of a few new concepts is more than enough, and we'll apply it soon. So we have now finished chapter 2, and I told you our goal is actually to get to chapter 5. Because in chapter 5, we will use our fundamental, or we will introduce the fundamental operations in a quantum computer. Like in a traditional computer, you have the NOT operation, the OR, as well as the AND operation. And in quantum computing, we have different fundamental operations. But we don't make it there directly, introducing new operations without actually understanding quantum theory. But stepping now directly from our maths foundations to quantum theory is also a bit tricky. So we first build something in between. It's a chapter on so-called systems, and our goal is to build quantum systems. From there, we explore the quantum theory more, and then we can build all the fundamental operations we need in a quantum computer. Once we have them, we can build algorithms, we can look at the theoretical limitations, we can see how all of this gets programmed and runs in a quantum computer and leads to concrete applications. So this is the roadmap, but it's still a bit of maths until we make it there. And our goal is actually to discuss quantum systems, because we need quantum throughout this course, but we are unable to directly build quantum systems, and we'll need a tensor product to assemble larger systems composed of smaller systems. So maybe let's first start, or before, look at probabilistic systems. And in order to understand probabilistic systems better, we start with deterministic systems. And then we become increasingly more complex because deterministic systems are very easy to catch. Then we make them probabilistic, and then we generalize the probability theory and make it to quantum systems. Concretely, we start with these classical systems. So deterministic and probabilistic systems are still classic systems. And we'll introduce a few notations and a few examples in order to get this. And once we have this, we can actually build quantum systems. And concretely, we will describe these concepts now in terms of graphs and matrices, which are two equivalent representations of the systems we're doing now. We want to build quantum mechanical systems. And for computer scientists, since this course is taught in a computer science department, if we use graphs and matrices, it's much more obvious to the audience than if we use some different concepts. I will again explain this in detail on the iPad, and we'll develop these concepts slowly together. First of all, as I said, it's not related to quantum because we first start with classical systems, but we need to be able to describe them and understand them. And once that's done, we will build quantum systems. So we need deterministic systems. In the deterministic system, what I show you now is all the stuff you would also find like this in the slides, which largely covers examples from the book. But I don't like just presenting slides over and over now. Rather, I want to develop these ideas with you. And in our deterministic system, we will describe this soon as a graph. We have 6 vertices in our graph. And I'm just putting the indexes there. And concretely, what I'm showing you now is a state of our system. Later, there will be transitions, but that's the next. Oops, one student said the iPad didn't work. I'm deeply sorry. I did the screen share. I don't know what went wrong. I just need a second. There's some strange issue I'm facing here. So, welcome back. Since the iPad had to update Zoom, we quickly had to interrupt the recording, but now we can continue. And now you should be seeing what you didn't see before because of the pending update. The screen share somehow didn't work for a moment. So thanks for pinging me here in the chat because I didn't see that. So what we have here is a state of a deterministic system. And our deterministic system, as we see here, has 6 nodes or vertices, if we see it from a graph perspective. And for now, what we want to do is we want to put in marbles in these positions. And for example, we could put 6 marbles in the first spot, 2 marbles in the next spot, then 1 marble, 5 marbles, 3 marbles, and 10 marbles. And this is now actually a state of our deterministic system, and we'll later see why it's deterministic. And we could describe this state as a vector. And we can write, say, the first element has 6 marbles, then 2 marbles, then 1 marble, 5 marbles, 3 marbles, and 10 marbles. But since this takes lots of space to use the column vector here, a notation we often use instead is just a row vector. We also see this throughout the slides quite often. If we use a row vector, it just leads to less vertical space. And so we can say 6, 2, 1, 5, 3, and 10. But transposed, because we always work with column vectors or mostly with column vectors in this course. And if we want to represent a column vector as a row vector, we write the row vector, but transpose it. So it means it's a column vector. And now what I want to do is, in this system, I want to model dynamics. What we will actually deal with is we will deal with different time steps, and we will wonder how we can move in one time step the marbles from one vertex in the graph to a different one. And for this, we need edges, because it's purely now a computer science representation dealing with graphs. We have these vertices already, and we can add edges to this graph now. What we can say is the marbles in position 3, they will just stay in a time click. So that's why we put the circle here, so they will not move them anywhere else. We will move from 1 to 2. We will move from 0 to 10 to 5. We move from 4 to 5. We move from 5 to 2. And we will move from 2 to 4. So this is just one example graph. It's a directed graph because these edges are directed. And we can now wonder, how can we actually use this dynamics and apply it to our state? What we could see is, if we do one time click, for example, 6 marbles in position 0 would be gone, and they would end in position 5. The ones in 3 stay, and over here it's a bit more complex. But we don't need to manually fiddle this out. Rather, we can try to express this graph from before as a matrix. And concretely, we will call this, we have this graph, and we will represent this as a matrix M. And the matrix M will be a 6 times 6 matrix, because we have 6 vertices. We'll use a very specific notation. It's very important that you follow them in the right order, because what we will do is we have a matrix at index ij, and this is 1 if and only if there is an edge from vertex j to I. And exactly that order, from j to I, not from I to j. Because we just used a notation that is used throughout the book. And what we see is, from this matrix, vertex 0 has no incoming edges, because from 0 there's only one outgoing edge and nothing coming in. So we put in 6 zeros because there are 6 vertices, and vertex 0 has no incoming ones. The one that is, for example, easier to describe is, we have the next row, for example. It's actually as similarly simple. The next vertex 1, only has an outgoing edge, but no incoming edge as well. So it's also all 0, because there are no marbles coming in to position 1 here, because we only have an outgoing edge. Now, position 2 has an incoming edge from 1 as well as from 5, the last one. So we can say, well, 2 has an incoming edge from 1. We put a 1 here. and 2 has an edge incoming from 5, so we put in a 1 here, and all the others a 0 again. Position 3 only has an incoming edge from itself, because we have this cycle. That means we put for position 3, which is the 4th row, the 1 here, because it's incoming, it's the cycle, but then all 0. Position 4 has 1 incoming edge from 2. So we put the 1 here, and the others are all 0. And now as your quiz, what would the last row look like for 5? You need to think about where are the incoming edges in position 5, and how would you represent this as the last row in our matrix? So one more row, and if you have the values, please send them to the chat, maybe without looking at the slides. We got the right answer. It starts with a 1 because position 5 has an income, or vertex 5 has an incoming edge from 0 as well as from 4. So we put another 0 here, and we put all the another 1 here, and all the others are 0 because there are 2 incoming edges. So this is exactly the notation. So we have a row, and the first row refers to the first vertex and where it has incoming edges from, not outgoing edges. It's all about incoming edges on that vertex. Don't mix that up. We will use exactly this notation throughout the course, because now we're using this for deterministic systems, but we can also use this later to describe probabilistic system, quantum systems, quantum gates in a quantum computer. We just need a little bit of time to make it there. And now the question was, one time click. If we have our start state, which we have denoted here, and we do one time click, how do the marbles move around? And we can very easily describe this because we say we have matrix M and we have our state X from the right. And here's one small problem. You have noticed I have used X as a capital. I always said states should be lower capitals, ideally bold, but I'm just using the same notation that the textbook uses. And then the book, unfortunately, for these examples, uses uppercase characters for vectors as well as matrices. I don't like this, but I didn't want to use a different notation, because then if you use the book for revision, you'll get totally confused. And what we are doing is here, we have matrix M, and we have matrix M, and I'll just copy the matrix from before, because we will do some calculations now after we have written above here the matrix. I'll just copy it. And we multiply from the right our state vector x. And x was before 6, 2, 1, 5, 3, 10. 6, 2, 1, 5, 3, and 10. And this is now quickly your task, that you multiply this vector from the right with this matrix M. Should be fairly easy because there are lots of zeros. And once you have the results, send them to the chat y is our result. So please multiply the vector with this matrix and we'll see the result very soon. And right now it's marbles, so it will be probabilities, and then it will be photons or electrons when we look at quantum. So step by step, this will become more complex. And it's correct 0, 0, and then it's 12, because 2 times 1 and 1 times 10, it's 12, and then it's 5, because we have 5 times 1, 5, and then we have 1 and 9. It's just linear algebra. And what we have done is we have used our deterministic system, and we have applied one time click, meaning in a time click, we move all marbles from one position or from that one vertex to the vertex where it's connected to. One time click. You can try this out on your own, but you will see 0 and 1 will be empty because they only have an outgoing edge, no incoming edge. In 3, everything will stay, and around here, it will just circulate. There is a requirement, and the requirement is that every vertex has exactly one outgoing edge. So 0 has an outgoing edge, 1 has an outgoing edge, 3 has an outgoing edge to itself, but we never have 0 outgoing edges and never multiple outgoing edges, because this would lead to some non-determinism if I don't know how to split up the marbles if I have multiple outgoing edges. But I can have multiple incoming edges. That's totally fine. Like, for example, 5 has incoming ones from 3 and 0. Now, and for this, I will simply move to the slides. We can try something more interesting now. We can wonder what happens after 2 time clicks. We have done this for 1 time click, and we have multiplied just before here, what we have done here, we have multiplied m times x. And the order is very important. M, our transition matrix, and from the right, vector x. And then we have this vector. And if we want another time click, we again could take our vector y and multiply it from the right with matrix M. And we apply one more time click. And we would see how it transitions. But what we can also do is we can have M and multiply M, so the transition matrix with itself. It's just a huge matrix multiplied with another huge matrix. But it's fairly easy because it's lots of zeros. So most of the elements will be 0 anyway. And if you multiply matrix with itself, a typical notation would be m squared. And what we can do then is we could, and we can try this out now together, for example, on the iPad again. I'll just copy paste here m squared. M squared is the following matrix that we got from the slides. So all zeros, the first 2 rows, and then 1, 0, 0, 0, 1, 0. And feel free to do these matrix multiplications at home for your revision to see if you can also derive them. So this is m squared, and our vector from before, x, so the start vector, was 6, 2, 1, 5, 3, and 10. And you can multiply now our x with m squared and share your insights here via the chat. And that would, what we are calculating is that we have taken 2 time clicks at once. So not just multiply m times x and get y. So this is like m times x would be y, and then we could take m multiply times y and have z, for example. We want to actually calculate z now, but not by first multiplying x times m from the right and get y, and then m times y, and then get z. Rather, we want m squared times x to take 2 time clicks. We got a suggestion for what the result looks like, 0, 0. Then the suggestion is we get a 6 times 1, and 1 times 3 is 9. The next one would be, we have our 5 times 1, because the 5 anyway stays in this cycle. And then we have the 2 times 1 and 1 times 10. So it's 12. And then we have our last one here, which is 1 times 1 is 1. So we have taken 2 time clicks. There's a question here if this is related or quite similar to the PageRank algorithm. So PageRank algorithm comes from a totally different environment, ranking websites or URLs. And what we do is we have each page and we connect them in a graph, how they link to each other. And we want to find out which is the most important one. And yeah, maybe it looks quite similar to this one here, but I think the PageRank algorithm has a totally different goal. And what we are doing here also doesn't necessarily converge because the stuff could just keep cycling. But I'm now in the limited time unable to talk a lot about the PageRank algorithm because it's also not relevant for this course. But thanks for the hint. So this is our deterministic system. And we will now finish deterministic systems and we'll make our systems slightly more complicated or slightly more complex. And for that, we'll move to probabilistic systems. And as I said before, there's lots of text sometimes in the slides. It's mainly also for your revision. Not necessarily for me to read this out or to present you with a lot of text. So we've worked with multiple marbles and we said we move the marbles around. From now on, we will work with probabilistic systems. And rather than moving many marbles around, we just consider one marble. And we don't know exactly where the marble is. Rather, we will work with probabilities of the probability where the marble could be. And in order for this to work out, we need now not deterministic states, but rather we use probabilistic states. And what we see here is if we have a simple graph, we say 3 vertices, so smaller graphs than before, we could have a state vector x, and we have these probabilities 1/5, 3 over 10, and a half. What do you notice if you look at that state vector? If you add up these 3 probabilities. You can always send this in a chat or also turn on your microphone if you want to share your insights. It's correct. This needs to add up to 1 because now we're dealing with probabilistic states, so the individual probabilities need to add up to 1. And what this means is there's like a 20% chance the marble is in position 0, a 50% probability the marble is in position 2 or vertex 2, and so forth. So you can only have a valid probabilistic state if all these elements add up to 1. And we could think about a probabilistic graph as well, because before we said that when we looked at deterministic systems, that our vertices can only have or must have exactly one outgoing edge. But when it comes to probabilistic systems, we can think about something different. We could say we have our 3 vertices, and there's a 1/3 probability that the marble goes from 0 to 1. There is a 2/3 probability that the marble goes from 0 to 2, and so forth. And we will now next try to describe this again in terms of a matrix, and we'll try to do some transitions in this system. Once we have done this, we can just make it slightly more complex and later make it to quantum systems. So I'll just redraw this graph we had just looked at. So vertex 0, vertex 1, vertex 2. And there's a 1/3 probability to go from 0 to 1, and a 2/3 probability to go from 0 to 2. Then if we look at vertex 1, there is this outgoing edge from 1 to 0, a 1/6 probability. The outgoing one from 1 to 2 is a third. Then we still have this cycle here with a half probability. And from 2, we have the outgoing one from 2 to 1. It's a 6th probability. And from 2 to 0, it's a 5/6 probability. We can now try to describe this again as a matrix. And I'll start with it, and then I leave it up to you what this matrix could look like. We see there's no cycle or circle here in 0, so it's just 0 has no incoming probability from itself, but there is a 1/6 probability incoming from 1 to 0, so 1/6, and a 5/6 probability coming in from 2 to 0. And now, having looked at this graph, I want you to continue this and provide me with the next 2 rows of our matrix M. And once you have them, send them to the chat. So the next row we got here in the chat is the 1 has this incoming edge of 1/3. So this is the 1/3. then 1 has this circle of half, and an incoming one from 2, for which the probability is 1/6. And the last row for the last vertex is incoming from 0 is 2/3. Then has incoming from 1, which is 1/3, and a 0 at the end, because there is no circle here. Almost correct in the chat, just 2 elements were flipped, but that's why we do this together. And also because today not many students are following the live session because we're not doing this at the usual time. I assume they are watching and hearing now the recording. So my advice is join the live sessions because we'll do these calculations together. We'll make it far easier for you to understand all of this. We will need this for all the quantum mechanics very soon. Now we have described our probabilistic transitions, and we can do again an example. So we have M from before. Now just write it down again. So 0, 1/6, 5/6, a third, a half, a sixth, 2/3, 1/3, and 0. And our X is just some probabilistic states. We could say 1/6, 1/6, and 2/3. And you could now have this start state. So there's a 2/3 probability the marble is in position 2, and the 6th probability for vertices 0 and 1, respectively. These are only probabilities, and then you have probabilistic transitions. You multiply X from the right with M, and you will then have the probabilities of where your marble could be after one time click. Now these are all fractions. You don't need to do this manually. You could use a calculator or just look into the slides. So there's a probability of 21/36 for vertex 0, 9/36 for the next one, and 6/36 for the last vertex. And this is Y. And this needs to add up to 1, but they all have the same denominator. So the numerators are 21 plus 9 is 30 plus 6 is 36. So 36 divided by 36 is 1. Now, this looks fine, and you could do the same things over and over again. You could have m squared or m cubed to represent multiple transitions and all of this as before. So this is nothing new. But we have discussed from the beginning that our states, the elements in a state, need to add up to 1. When we look at our transition matrix here for the probabilistic system, is there something you notice in this matrix M? Some property, if you look at its rows and columns. If you have something, maybe just raise your hand or turn on your microphone or use the chat. If there is some property you're noticing in this matrix. So I see some clap. Yes, you raised your hand. Please go ahead.
Sorry, by mistake, instead of raising my hand. So I think each sum is 1.
Mm-hmm.
Like 1/6 plus 5/6 is equal to the whole number 1. 1/3 plus half plus 1/6 is equal to 1. And 2/3 plus 1/3 is also equal to 1.
Exactly. That's correct. Each sum and each row and each column, they sum up to 1. And this is not just a coincidence, it's actually required. Concretely, we will deal now with doubly stochastic matrices, and doubly stochastic matrices are matrices for which we have real value entries. So we're constrained to real values because it's probabilities between 0 and 1, and the sums of the rows and sums of the columns are all 1. Um, and this is a consequence of the following constraint, because we are constraining our graphs to two conditions: that the sum of all weights leaving a vertex is 1, and the sum of all weights entering a vertex is 1. And then we deal, as a consequence, when we apply these constraints to our graph, we will deal with so-called doubly stochastic matrices. And these are key. If we don't use doubly stochastic matrices, this will not be working anymore, and we won't be dealing with proper probabilities. We have always so far used our matrix M and multiplied a column vector from the right to do one-time transition or one-time click into the future. But you can do something else. We can use our matrix and we can multiply a row vector from the left. We are unable to multiply a column vector from the left because then the dimensions don't fit. But we can multiply a row vector from the left. And we will get a result which is also a row vector. What could this lead to? Do you have any suggestion what is happening if I'm multiplying a row vector from the left rather than a column vector from the right? Any guesses what could be happening in this system? Again, feel free to turn on your microphone and guess or send something in the chat. Yeah.
The order will change if we start from the left.
What order will change?
The order of the answer coming.
Okay, but if we said we do one-time click into the future by multiplying from the right, what could be happening if I'm multiplying from the left?
It will be the same as mx.
No. Oh, fine. We'll discuss it. I just want to see if someone wants to guess. Well, if I'm multiplying from the right and I go into the future, one more time click, maybe if I multiply from the left, I'm doing the opposite. Maybe I go back in time. This maybe could be a suggestion, but we'll investigate this more now. What we can also do is we have our matrix from before, M. We've seen it quite a few times now. And maybe to make it fully clear, I'll do this on the iPad. So we'll develop it step by step. Rather, we need to flip around between these slides. So screen share is coming again. So we have our matrix M, and we had it up here, but I guess I need to copy it again that I have enough space. So my matrix M was this one here, 0, 1, 6, 5 over 6, 1/3, 1/2, and 1/6, then 2/3, 1/3, and 0. Now I can transpose the matrix very fundamental operation that we've practiced before, and now we need it again. And if I transpose the matrix, the transpose will look as something like this. You all know how to transpose. And we can try to plot this graph now. Before, and just to compare them very well, I'm putting here on the left the graph for the original matrix M. And even if I need to copy it, I guess it's essential if we understand it and we can compare it with just the old graph from before. Something like this. Hope this. If you ever see any typos or mistakes that come in by accident, please ping me. Now, if I visualize the graph for the transpose matrix, let's see what that looks like. Because these ones here, and in fact, we're just flipping them. So we had a 1/3 going from 0 to 1 and a 1/6 going from 1 to 0. We just flip them. So we have a 1/6 from 0 to 1, and from 1, 0, it's a 1/3. It's exactly the same for the others. It's all well formatted in the slides. And by the way, we also needed this one here, obviously. So this one doesn't change. Then we have a 1/6 here and a 1/3 here. So just the opposite direction as before. And a 2/3 and a 5/6. In the slides, it's printed in a nicer way. So what we're doing is we're just reversing the edges, in fact, when we transpose this. And reversing the edges is like traveling back in time or having this marble roll backward. And we can try out some of this. And if you remember laws of transposing and multiplications, I also have a slide for you just as a revision, may ring some bells from your linear algebra introduction. If I have, say, something like this here, M transpose times W transpose. Remember the W from before. The W was this row vector, and I wanted to go back in time by multiplying this state from the left with my matrix M. I got this one. And what I'm doing here is I'm taking my W and I transpose it, so I have a column vector, and I multiply it from the right with my matrix transpose, which is just going back in time them. I'm getting the same as we've just done before. Because there's this time symmetry, we said before I have my row vector W multiplied with M from the left. I got a vector. Concretely, I got a row vector as a result. And if I transpose this row vector, I have a column vector, and it's the same column vector as if I take my row vector transposed and multiply it from the right with that transposed matrix. What this gives me is a time symmetry. So multiplying with m from the right goes from time t to time step t plus 1. Multiplying on the left takes a state from time t to t minus 1, where t plus 1 goes back to t. So this is a fundamental concept of time symmetry, which we have now discussed for probabilistic systems, and we will desperately need it later for quantum systems. And these unitary matrices that we've introduced earlier, you remember these with this dagger, they will play a crucial role in quantum systems to model this time symmetry. We're not in quantum systems yet. That's why I first showed you what this looks like in probabilistic systems. And these things we've discussed before, like for a deterministic system, if I have m and I multiply it with itself, I'm taking 2 time clicks. I can generalize this with a variable k, and m to the k means I multiply m k many times with itself then. And I make k time clicks. And you can apply this as, you can try this out as an example. So you have m squared, which is m times m, some nasty fractions to deal with. This would be the matrix representations for 2 time clicks in the probabilistic system. So not quite different to the deterministic system. And there are a couple of examples we will investigate now. And I guess I'll derive them again, step by step on the iPad, because then it's also more fun for me than just talking about slides, and we'll develop this step by step together. Concretely, we will look at an example that is in a literature referred to as the stochastic billiard game. And later there will be a quantum billiard game. And the stochastic billiard game, we say we have A, which is a transition matrix for the following graph. Now, and this is an example you should remember very well after we've discussed it, because later or next time we'll see a quantum version of this. So we have 4 vertices, 4 positions, and we have very simple transition probabilities. We can go from 0 to 1, from 0 to 2, from 2 to 0, from 1 to 0, we can go from 1 to 3, from 3 to 1, and from 2 to 3, and 3 to 2. And all these transition probabilities that for these edges we have just drawn, the probabilities are 1/2. We can try to represent this as a matrix. So we see 0, position 0 here, has incoming ones from 1 and 2, which are the probabilities 1/2, but nothing incoming from 3, and not from itself. So it's 0, 1/2, 1/2, 0. We look at vertex 1, has incoming ones from 0 and 3, probabilities 1/2 respectively, but not incoming from 1 or 2. And then we look at the position of vertex 2, incoming ones also from 0 and 3 with 1/2 probability, but not from 1 or 2, which is itself. And for vertex 3, we see it has incoming ones from 1 and 2. Does this look like a valid matrix to you that we can use for probability or for probabilistic systems? Maybe thumbs up, thumbs down, what you think about this matrix, if it looks valid, and if it looks valid, maybe tell us why, if you remember the correct term we have previously introduced, and feel free to. So we got a thumbs up, which is very good. It's correct. It looks correct, and maybe you remember the word, and now we got it in chat. It's doubly stochastic. So that's a term you need to remember. A doubly stochastic matrix. And we can try this now. We can say we have A and we multiply it with a start state where we know for certain that the marble is in vertex 0. Something like this. And let's try it out. What happens? This is your task now. Multiply our vector, our start vector from the right with our matrix A. And if you have done this multiplication, let us know what the result is. We get a 0, a half, and a 0. So after one time click, we know the marble is for sure in position in vertex 0. After one time click, there is a 50% chance it's in vertex 1 and a 50% chance it's in vertex 2. Now we can continue this with a second time click, and we have our A, and we just multiply it with the state we got after one time click. We'll try this again and see what happens. So our matrix is again the one as before. This is your task now to multiply our state after one time click from the right with our matrix, and we'll see what we get. That's correct. It's a half, 0, 0, and a half. So what this means is we start with the marble that is guaranteed in position vertex 0. We do one time click. It's 50% chance in 1 or 2 each. And we do another time click, and then it's either in position 0 or position 3, each with a 50% chance. And if you continue it from there, this will just bounce back and forth between the vertices 1, 2 as the one pair and 0, 3 as the other pair. This was just one example to practice the mechanisms we had studied, but we will also come back to this in the next section when we look at quantum mechanics, and we will look at a quantum version of this example. We will look at something else now, another example, which is a simplified example in the probability theory. And for now, remember just this probabilistic billiard game, so the one we've just done here, because we will come back to that with a quantum version. And the quantum version will behave different because it will take effect of some quantum mechanics and will behave quite different, but you'll see this in the next section. We will now look at the double slit experiment. Who of you remembers the double slit experiment from a physics course, say in high school, or maybe in a physics course you have taken at university? Maybe thumbs up, thumbs down, if this is something you have come across, you remember. So some remember, some don't. No problem at all. So the double slit experiment is something we'll investigate in great detail when we look at quantum systems. But now with probabilistic systems, we'll have a simplified double slit experiment. What we will do is, we will have an experiment and it has two slits in the wall. And there's a shooter that is good enough can have a shot that the bullet always goes through one of the slits. There is a 50% chance the bullet will travel through the top slit, and there's a 50% chance the bullet will go through the bottom slit. And once the bottom is through a slit, there are 3 targets to the right of each slit where the bullet can go with equal probability. So I'll visualize this to you. So we have here our gun, and we have a 50% chance the bullet goes through the first slit, and a 50% chance the bullet will go through the second slit. And once it has gone, say, through the top slit, there's a 3rd chance each it will go in the first target, second target, or third target. And if the bullet goes through the bottom slit, there's again a 1/3 chance it goes into the 3rd, 4th, or 5th target, respectively. And this is just a simplified double slit experiment because we'll see it again as a quantum version. It will keep us quite busy to describe quantum mechanical effects. But here it's just a probabilistic double slit experiment. And we can try to describe this as a graph. And I think I will again describe the graph step by step, because we will also need to turn the graph into a matrix very soon. Somehow, each time I open the Notes app today, it's always starting from the top, and I need to scroll down, which is quite bothering. And so if we describe the probabilistic double slit experiment in terms of a graph and the positions where the bullet can go, the bullet starts in position 0, so in the gun. And then we shoot, and there's a half chance it will go through. Oh, let me just change this. There's a half chance it will go to the first slit, the top slit, or a half chance it will go to the other slit. So this is the top slit, this is the bottom slit. And from there, say from the top slit, there are these 3 targets we had just looked at. This is vertex 3, vertex 4, vertex 5. Each of these probabilities is a 1/3. And once it is in there, it will just stay. So the experiment is over. So once it's in position 3, it stays there if you take more time clicks because the bullet has hit the target. Same for vertex 4, vertex 5, which are these top 3 targets. But then from position 2, there's also a 3rd chance it can go to vertex 5. A 3rd chance it can go to the next target. And again, a 3rd chance it can go to the last target. And ideally, we just put the 1 probabilities here that it's complete. What we notice is vertex 5, which is the third, the middle target, there are two ways we can hit it, either through the top slit or through the bottom slit. And we will describe now again this system that we have, or this double slit experiment, this probabilistic system as a matrix. It will be a bit of a lengthy matrix, but I still at least want to do this with you once, that we have another way to practice how these matrices work. They're all written down in a very nice way in the slides. So what we see is for vertex 0, there are no incoming edges, and in total, we have 8 vertices. So these are 8 zeros. What do you think the next row could look like, or the next 2 rows of this matrix, without looking at the slides, please, because there you would see what the solution could look like. The next 2 rows will address the vertices 1 and 2 in the graph. I'll see if there's something in the chat. And that's absolutely, or one of the answers is absolutely correct, because it will look something like a half, because this is for vertex 1, there's a half probability coming in from 0, and it's the same for vertex 2, which is this one here. All the other entries are just 0 because they don't have any other incoming edges. Now, the next row would address this vertex here. And this vertex, vertex 3, and there's a question here about the property of this matrix. That's a question that I just got in the chat, which we will address later, because it's the right hint, but I'll discuss it once we have built the whole matrix. And we will see vertex 3 has an incoming edge from 1, and it has this circle. So incoming from 1 means we have a third here, this 0, and then this 1, and then all these zeros, and a 0 here. Then the next one, which is this one, looks pretty much the same. It's a 0 and a 1/3 and more zeros, and then these ones, because these ones are just these remaining circles here, and we can also try to put them in already. What is interesting is this element here, because it has 2 incoming ones from vertex 1 and vertex 2. So these are all these 2 1/3. And the simpler ones are these 2 remaining ones, because they have an incoming one from 2. So we have the 1/3 here and the 1/3 here. And just adding the correct zeros, and I have all the zeros on the right spot. So this matrix describes the transitions for this probabilistic system, and we got a very good hint in the chat, which I like a lot. The matrix is not doubly stochastic. This is not a proper probabilistic experiment, because a double slit experiment is not probabilistic. Double slit experiment is a quantum experiment. So it's only a simplification of the double slit experiment. But we will use this simplification now to observe something. And then we'll try to observe this again in the quantum version. And what we try to observe will look different in the quantum version because we will use quantum mechanical effects. What we have just discussed is this one here. So here it's well formatted, and it's all from the course book, these examples. And what we can do is we have our transition matrix B for this graph. We can also multiply B with itself to describe two time clicks, because what happens in the double slit experiment, and there's a question I shall explain. Why are these one entries in here? These are these circles. Because I said once you're in 3, 4, 5, 6, or 7, the experiment is over. So if you try to do more time clicks, you will just stay in 3, 4, 5, 6, or 7 because the experiment is over. You have hit the target. And when we start the experiment with a start state, so the start state is the bullet is guaranteed to be at 0, and we take one time click, we have a 50% chance to be in 1 and a 50% chance in 2. And if we take one more time click, we are in the targets. And if we want to do both time clicks with one matrix, we need to multiply B with itself. We've seen this before. And if you multiply B with itself, I'll spare you this now. B squared, which is B multiplied with itself, looks something like this. And we can now wonder about our start state. The start state is the bullet is 100% in position 0. So this is the start state, just a 1 and then all zeros for the other states. And we can multiply x from the right with B squared. So B squared is 2 time clicks, and we multiply x from the right because we want to go into the future. We will get something like this. We have zeros in the first 3 entries because the bullet, I'll show you this, the bullet cannot be here or here anymore because we have taken 2 time clicks. The bullet has to be in one of the targets. And concretely, we will see there's a 1/6 chance it's in the first target, a 1/6 chance in the second target, a 1/6 chance in the fourth target, and a 1/6 chance in the fifth target. But there's a 1/3 chance we are in the third target because it's this one here that has incoming edges from 1 and 2. You can try out all of these calculations and see that this sums up, or you calculate B squared on your own. And if you continue like you do B cubed, B to the 4, this will not change anymore. So the note in the comment here is right, because the experiment is over and we have these ones in the diagonal. But this is not a doubly stochastic matrix. Don't forget this. It's just a simplification because the double slit experiment that we will witness later, or probably next week, is a quantum experiment. Here we've only simplified it to look at a probabilistic experiment. So we will see this very soon. And we're done now with probabilistic systems, and we still have some time today to actually look into quantum, because this is a quantum computing course, not a deterministic computing course, not a probabilistic computing course. It's a quantum computing course. And we'll now work with quantum systems from now on. So we will leave the world of deterministic systems, we leave the world of probabilistic systems, but it was helpful to build these systems first. And I'm asked to briefly show how the adjoint matrix would be calculated for a 5 times 5 matrix. We can do that. We can do this as a quick interruption, just as a revision. Absolutely fine. So remember the adjoint. I'm happy to put in a revision. So we have A, just as a reminder, which was A, B, Z, and D. And what you want is the adjoint, so A dagger, and this was the conjugate of A, the conjugate of D, and then the conjugate of uh, B and C, because we have just transposed this. And now your question is, we have matrix B, and we have these entries. So we could say A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. And I understand what you want is B dagger, right? Because you wanted the, can you just confirm that this is what you want, that you want the adjoint matrix? Um, yeah. So the adjoint is the B dagger. So the diagonal stays, but you have the conjugates. So M, S, and Y. Uh, but you said not the dagger, the adjoint. Well, the dagger is the adjoint. Do you mean the transpose? Maybe just to confirm if you move. Okay, we'll do this with the conjugate. So because I guess what you asked for was maybe the transpose. And we'll see this now. So the diagonal stays, but we have the conjugates. And then it's just the transpose of a matrix. So a super simple operation. So we turn rows into columns and columns into rows. So we have A, F, K, P, and U. And we take the conjugates, and here B, C, D, and E, and the conjugates, and so forth. So you just turn rows into columns and columns into rows. So and you would just continue like this for the remaining elements, and we take the conjugates. Are you okay with that? Good. So this was just a quick revision or update on the conjugates, but we will need this stuff. So if you have any questions in between, any revisions needed, I'm most happy to help. Now we will look at quantum systems. And the quantum systems will be super interesting because before we have worked with probabilities that are real numbers between 0 and 1. And we will deal now with complex numbers. And we have complex numbers throughout our quantum systems, like complex number Z. And something that is important is the modulus of the complex number squared. And we learned last time how to calculate the modulus of a complex number. And if you take the modulus and you square it, this too will be a real number between 0 and 1. Not the complex number will be a real number, but the modulus squared. And this will be a very important property throughout this course. And you're probably wondering, why do we need to change now to complex probabilities? And maybe you remember I said this last week, but today in the beginning of the revision as well, quantum mechanics is eventually a generalization of probability theory. And rather than dealing with probabilities between 0 and 1, we will deal with complex numbers, which are complex probabilities. And then something interesting can happen as an example. So let's say we take the following example. We have a complex number, C1, which is 5 plus 3i, and the second complex number, which is minus 3 minus 2i. And now let's look at C1 squared, so or the modulus of C1 squared. Remember, the modulus was 5 squared plus 3 squared. But so far we have not put in, because what I've calculated here is the modulus, but I need to square the modulus. So modulus squared will be, in fact, we just remove or we eliminate the square root. And later you'll see why we need to do all of this. But this will be eventually 25 plus 9, which is 34. And the modulus squared of C2 is, again, 3 squared plus 2 squared. So this is 9 plus 4, it's 13. So what you will notice is if you add these modulus squared, then you add values on top. But if you add the complex numbers and you take the modulus squared, they may be getting smaller because they can cancel out each other. For example, see something like this. We have C1 and C2, and we take the modulus squared of that sum. So we just add the two complex numbers, 5 plus 3i plus minus 3 minus 2i. So this will be 2 plus I. This is our complex number. And the modulus squared of this is 5. So we see if we add two complex numbers and we take the modulus squared, that value can be less than if we add up the modulus squared of the two individual complex numbers. So the complex numbers allow us that these probabilities can cancel each other out. And this is a super important property in quantum mechanics, that these complex numbers can cancel each other out. There's a special term for this canceling out, and the fact that complex numbers may cancel each other out when added has a well-defined physical meaning, and this is called interference. A very important, interference, not inference, interference. Inference is something different, but interference. So don't mix up these two words. Inference and interference are not synonyms. They're totally different words. And interference is a super important property in quantum mechanics that we investigate in the next few weeks, and we will need it for quantum computing. Now, remember our systems we have built so far. We had deterministic systems, which we had multiple marbles. We had probabilistic systems. We had one marble, but didn't know where it was. We only had the probabilities. And we said that these probabilities of the individual positions need to add up to 1. Now, if I have a quantum state, and all these things I'm saying now or writing down, you also find them in the slides for your own revision if you wish. I have a quantum state now that is called X, and I don't want to write down a lengthy column vector that needs a lot of space. I just write down a row vector and I transpose it to highlight we're actually working with column vectors. So our quantum state has 3 elements. The one is 1 divided by the square root of 3. Then 2i divided by the square root of 15 and the square root of 2 divided by 5. What is important now, that we always deal with complex numbers, even if they only have a real part it's still a complex number, and we need to calculate the modulus squared of each of these complex numbers. You now have a task. I want to know from you, what's the modulus squared of 1 divided by the square root of 3? Once you have done this, we need the modulus squared of 2i divided by square root of 15. We got the right answer. It's 1/3. What's the next one? The modulus squared of 2i divided by the square root of 15. And then we also need the modulus squared of 2 over 5, the square root of 2 over 5. So we got the right answer now for 2i divided by square root of 15, and we take the modulus squared. This is 4/15. And the last one is a complex number. Again, a complex number only with a real part. It's 2 divided, or 2 over 5, the square root of this, and the modulus squared of this, it's 2 divided by 5. Now, if you add up these three values, 1/3, 4/15, and 2/5, this adds up to 1. Because the condition for quantum states is that the modulus squared of the entries must add up to 1. Just to show this also in a well-written way, I'm opening here my slide deck. So the definition of a quantum state is that the sum of the entries in the state, or the sum of the modulus squared of the entries, must be 1. And this is just our quantum state from before, and the modulus squared of these entries adds up to 1. So not the entries add up to 1 as before for probabilistic states, but the modulus squared must add up to 1. That's a valid quantum state. And now we can just use the framework from before and build increasingly more complex quantum states. We also need to be thinking about dynamics, because we have states and then transitions. And we will now not just use complex numbers in the states or in the state entries, but we will also put complex numbers into the weights of our graph for the transition. And we don't insist anymore that this transition or adjacency matrix of the graph must be doubly stochastic. That's something we've asked before with probabilistic systems. Now with quantum systems, we require that these adjacency matrices of the graph, so the transition matrices, must be unitary. You still remember the concept of unitary from before? Maybe thumbs up, thumbs down, because this is what something we did earlier today. If you still remember the concept of a unitary matrix, thumbs up. If you don't remember, thumbs down. But we only got thumbs down, some thumbs up, so that's perfect. Remember the unitary matrix, a matrix U is unitary if U dagger times U is the same as U times U dagger, which is the identity matrix. And again, I will present you with a few of these examples now in here on the whiteboard. We can have now quantum systems. And one example here could be, we have vertex 0, vertex, well, do it a bit smaller so it will fit. So we can put a matrix to the right and save some space. And the example here is, so we have a cycle or circling here, a 1. We have this one here with the probability of 1 divided by the square root of 2. We have this one with the probability of I divided by the square root of 2. I didn't come up with these examples. It's from the book, but we'll soon see that this is actually a useful example. And this is minus I divided by the square root of 2. And this last transition probability is 1 divided by the square root of 2. Something you will see often in this course, or when you deal with quantum mechanics, you wonder probably why are these probabilities not 1 divided by 2, but 1 divided by square root of 2. This is something you see quite often, also with square root of 3 rather than a third. It has to do with the modulus squared, because when you have 1 divided by square root of 2, you take the modulus and you square it, then the square root will disappear. That's why, and this wouldn't work if it was a 2 or something, because then all these probabilities wouldn't add up adequately. Now, I want you to provide me with matrix U. And matrix U is the adjacency matrix for this graph, or just the transition matrix we will need. If you have U, please send it here in the chat and we'll compare it. And just that you have a good start, I'll start with the first row for now. So 0 has an incoming edge from itself, which is this 1 divided by square root. So this one we've just seen. And it has an incoming edge from vertex 1, which is, again, 1 divided by the square root of 2, and then a 0. If you have a suggestion for the next row, please send it here in the chat. So it's not more difficult than before. It's just complex numbers that we're dealing with. We got with suggestions like minus I divided by the square root of 2, which is this one here, incoming from vertex 0. Then we have this one, which is the I divided by the square root of 2 and a 0. And then 0, 0, I. Now, actually, you see, we've just developed this step by step. We started with deterministic systems and probabilistic systems. And then we got quantum systems. So not very difficult, or not very much more difficult than before. And this is what we have just done together. Now I want to do a transition, that I take our start state from before and I multiply it. So our start state, we've seen before, a valid quantum state. Because here it's also these are also probabilities, but they're complex numbers, because we also don't know in which position. It's not a marble anymore. Now we're at a quantum mechanical level. So this could be an electron or a photon, and we just don't know say a photon, and we don't know where it is exactly, but we have probabilities of where it could be, and these probabilities are now complex numbers. And we have this valid start state, and we do one transition with our quantum system. So we multiply our state x from the right with the matrix U, and we get something like this. It doesn't look very neat. That's why I'm not trying this out with you now and try to normalize them or make them look nice. Rather, just bear with me that this is the result if you multiply this vector with this matrix. Um, Probably the simplest example you can see is this last row. You have this last row, you multiply it with this vector. So it's just I times the square root of 2/5. And this is why. And since or if our matrix U is unitary, and we always require our matrices from now on to be unitary, if they are unitary, then our state will also be a valid quantum state. Um, what you can also do is, so you can try to convert our matrices, our unitary matrices that we have now, into doubly stochastic matrices. And in fact, what you can do is you can calculate the modulus squared of all the complex entries in our matrix. So this matrix from before here, and you can easily test if it's unitary on your own. And if you take the modulus squared of every entry in our unitary matrix, this will eventually lead to a doubly stochastic matrix. So this is just a link to before, where we've seen doubly stochastic matrices, and now we can convert them. And there's a question, the question is, where is this a probabilistic system? So we've dealt with probabilistic systems before, and now we've taken it one more level because we're dealing with quantum systems, and quantum systems are inherently probabilistic. But we're not dealing with real probabilities between 0 and 1. Rather, we're dealing with complex probabilities. So it's just an extension of the framework before. And in our start state, we don't know where the photon is, but rather we have these probabilities. As before, we had probabilities for where the marble could be, but these probabilities were real values between 0 and 1. And now we have complex probabilities. So it's just an extension or a generalization of probability theory. And these transitions here are also probabilistic in terms of complex numbers. So I hope this answered the question. And we've now seen we can convert our unitary matrix into a doubly stochastic matrix by simply taking the modulus squared of every entry. And it's easy to see that this matrix here is doubly stochastic because all the rows and columns add up to 1. This next step is also something I will show you on the iPad. Then it's easier to follow. The unitary matrices are key to what we want to do in quantum computing or in quantum mechanics in general. Imagine you have a state V, and our state V evolves because we multiply it from the right with a unitary matrix U. Then we have done an operation, and later in quantum computing, U could be some fundamental operation. Like you have an AND in a traditional or in a binary computer. You have different fundamental operations in a quantum computer. And we have done this, but the way quantum computers work, and in order to make this run efficiently, sometimes at a later step, we have to undo some operations. And this is something you cannot really do in general in binary computers. You can undo a not because you can just apply a not after a not and you've just undone it. But you have, for example, an AND. You cannot undo an AND because an AND, you have two inputs and one output, and you cannot infer from the output what the inputs were. But in something that we call reversible computing, we can do this. And quantum computing is inherently reversible because I have my U times V, which is some new state. So this has led to some new state, but I can take this new state and multiply it from the right with U dagger. And this will eventually, so U times U dagger just gives me the identity matrix. And then I have my state, well, didn't look nice, sorry. Then I have my state V. And this here is neutral because it's just the identity matrix. So using these unitary matrices, I'm able to undo operations. And this is something will become more obvious in a few sections in this course. But just to show you why we need unitary matrices, because then we can undo things, something we cannot do, at least in general, in binary computing. Just a small hint on the side. Imagine, so we have I3. So I3 is this matrix here. We can also visualize this one as a graph because it's also a transition matrix, even though it doesn't change anything, but can be visualized. So we can have here 0, 1, and 2. And we just have these loops, which are 1, 1, and 1. So we can even visualize the identity matrix if it's a transition matrix here as a graph. We have, and I'll just copy from, because I need this down here again. We have this graph from before and this matrix. And I'll just copy it down here, then we have enough space for it. And then we will apply the dagger operation and see what it leads to. So I'll just copy it here again. We have our 0, our 1, 2. So it's just the one from before. And this was 1 divided by the square root of 2. I divided by the square root of 2 minus I divided by the square root of 2 and 1 divided by the square root of 2. And we saw that this matrix was this one here, U. You've derived it before, so I'm just copying. And now, again, another quiz for you. What is U dagger? I want you to provide me in the chat with U dagger. And then we'll see what U dagger actually looks like if we visualize it as a graph. Remember the adjoint, we transpose it and we apply the conjugate to every single element. So probably the simplest one I can do as a hint for you is this one here. It stays where it is, but it becomes minus I. And these zeros just stay where they were because they just flip, but eventually there are zeros. And this 1 divided by the square root of 2 stays because it's just a real component. There's no imaginary component. And I want you to provide me with these 3 remaining elements. If you have the first remaining element that comes up there, tell me in the chat, and then the others. Or you can provide the whole matrix in the chat or the first row as you wish. And this is perfectly correct. It's I divided by the square root of 2 because it was this element, and because of transpose, it goes there, and the sign changes from negative to positive. That means this element comes down here and it's just a real component. And the last element, we also got this right. We have it stays where it is, but it comes minus I divided by the square root of 2. And this it undoes the previous operation. And if U is unitary, and then we have U dagger, and we multiply these two matrices, this will lead to the identity matrix, something you can try on your own. But we can also try to visualize this, this new matrix. And we start with the simplest part. So we see before this was an I down here. So it's a minus I now. So this is the 0, the 1. This, what we saw here, it just stays. It's 1 divided by the square root of 2. And like this one here, so this becomes minus I divided by the square root of 2. And then we still have these transitions here. Oops. And eventually the transition from 0 to 1 will be 1 divided by the square root of 2. That was this one here before, now it's up there. And the other one will be I divided by the square root of 2. So now you have the graph visualization of this matrix. And probably you remember from before when we looked at probabilistic matrices, when you just write this maybe down again, or no, I'll go back to the slides and we briefly look at as a revision at the probabilistic system. And we had something like, I just need to find it. It was this one here. We said if we transpose M, was concretely this one. So this was the probabilistic matrix. If we transpose it, we can go one time click back in time. And we have looked at this time symmetry that we go from t to t minus 1 if we transpose M or if we multiply the row vector from the left to M. And we can do exactly the same now in a quantum perspective with our unitary matrices, because we have U, and with U, we move one time click into the future, and with U dagger, which is also a transpose, but it also applies the conjugate operation to the elements, we go back one time click. And if we multiply U with U dagger or U dagger with U, this just undoes this, and we don't move at all in time, and we have just undone the operation. Is that something that makes sense to you from what we have done now? That with U, we move one time click into the future, and with U dagger back into the, back one time click. Because it just undoes what U does. If this is something you feel you have understood, maybe thumbs up or thumbs down if it's not that clear yet. But I see thumbs up. That's perfect. So we're now at slide 99. Slide 100 is the quantum billiard game. Today we have introduced the probabilistic the probabilistic billiard game. And we've done lots of stuff today because just as a revision, we started with a revision of last week. Then we've looked at linear algebra, then at complex linear algebra. And then we started building deterministic systems, then probabilistic systems. And we've seen how we can move in the future, how we can move back, what the transpose leads to, what's the difference between multiplying a column vector from the right versus a row vector from the left. There's a time symmetry. And then we've moved into quantum systems and we saw new constraints like the sum of the Modulus squared of the elements needs to be one of a state. We've seen that the transition matrices don't need to be doubly stochastic in quantum, but they need to be unitary. And we've seen that with unitary matrices, we can move one time click into the future, and the adjoint or the U dagger, we move back in time because they just undo this. Was lots of stuff, I know this, and you should take enough time for revision. And for the ones watching the recording, you should join the live session if you're from our university, because then you can join also the exercises. Next week, we will continue with quantum systems. We look at the quantum billiard game, a quantum version of the billiard game. But since we introduced the billiard game today, you need some time for revision. And we will look at the quantum double slit experiment and how it differs from the actual or from the simplified probabilistic one. We will look at that and we will compare them. And then we will use the tensor product to assemble systems. So we have multiple systems and we can compose them together by using the tensor product, also a concept we have introduced today. This is about, like, you see it, 23, 22 slides or something of more theory about quantum systems and assembling systems using all the maths from today. And then we can look a little bit more into quantum theory because we need to understand quantum theory a bit more also from a physics perspective. And then we have all the foundations to build quantum or the fundamental quantum operations. So, but in terms of maths, we've done all the maths we need for this course, or most of it, I guess, almost all of it. And you have to be familiar until next week with this mechanism we introduced of these graphs, these transition matrices, how to multiply states with that, how states are valid or invalid. And the deterministic ones and the probabilistic ones, they're not further important to this course, but they are important to understand how this mechanism works so we can use this mechanism for quantum systems. Are there any questions from your side now towards the end? If there are questions, just raise your hand here in Zoom. If you're okay, maybe just a thumbs up or some clap or whatever. I know this was tough today, but over time it will become more obvious and we just need more practice. And all these concepts we've introduced, we need them for the fundamental quantum operations. So make sure you're familiar with them. And I know it took quite long today until 7:20 p.m. or something, but next week we'll have the regular schedule on Friday afternoons. I already wish you a good weekend and see you next week. Bye bye.